bring that back. Maybe, if anybody, thank you. Okay, so let me start with announcements. This is how I almost always start class, just to make sure everybody's on track, knows what needs to be done, so forth. So today is the last day if you want to do our department's assessment test. Remember, it's on Blackboard. The rules are there. I already gave you a warning about it that, yeah, you're probably not going to know how to do it, but please try. You need to at least put some answers down, even if you just go with your gut, if you want to do it, okay? But it needs to be done today because it needs to be a pretest before we start to learn much physics. But if you do it, remember what I'll do is I'll drop your lowest 2 quiz scores at the end of the semester. Okay? So today's the last day to do that, by the end of the day. Next thing that's due is another set of Wiley Plus problems. You've noticed that if you've been on the site. And this set is due, today is Wednesday, tomorrow at 11:59 p.m. Eastern Daylight Time. Okay. On Wiley Plus. And if you've looked at it, it's now, we've gone into chapter 2. These are problems on chapter 2. Okay. Remember, the physics tutor is available on Monday evening and Wednesday evening. So this evening, Dave Shaibi will be available from 6 to 8 p.m. And I sent you a link, 2 links, one for the Monday session and one for the Wednesday session. So if you want to talk to the tutor tonight, go back to that email and make sure you click on the one for Wednesday. It's a Google Meet invitation. Okay, and it will be valid, that one will be valid for every Wednesday from 6 to 8. Okay. Also remember, I have office hours. For today, my office hours are from 2 to 4. Tomorrow as well. I think what I'm planning on doing is just hanging out in Blackboard Collaborate. So you just go to our Blackboard site, and on the left, it says Collaborate, and it says Join Session. That's like going into a classroom. And you click on that, and that's where you and I can communicate. However, I may not be watching that every second of the office hours, so you might want to shoot me an email, say, hey, can you meet me in Blackboard for a question? That makes sense? You can always email me at other times as well, and I will answer as soon as I can. But these problems are the kind where you have to sit and think about them a while. They're not just going to be plug and chug, because that's not really what physicists do. Okay, physicists reason about the natural world. So there's reasoning involved. And the problems almost always take a little bit of time just to sit and think about, wait a minute, what is this problem asking me? Okay. But in doing that, you're developing your reasoning skills, which is very important. Okay. So these take time. So my advice would be for this set, which is due again tomorrow evening at 11:59, don't start, at 9 o'clock tomorrow night. You won't get very far. All right. I'm just saying that in general. That's just the way physics is. It's a challenging thing that takes practice. Okay. Also, as you know, hopefully we're starting to develop a rhythm here to how this is all going to go. I'm sending you pre-lecture videos. The point is to watch those before you come in here. So I sent you the one for today earlier, yesterday. Okay? You want to watch it before here. And in fact, if you've watched it, you've noticed at the end, I got a class engagement question for you. You have to give your answer on Blackboard. Okay? You can still do that even if it's after the fact, but the goal is to watch the pre-lecture video before lecture. Okay? Yes, question. 2.2. Okay? The way the other way you can look, the other thing you can look for on the video is even in the name, in addition to the name like video lecture 2.2, it should have the date. Okay, so you would want the one that for Wednesday, August 26th. Okay. Yes. Yeah, that's Blackboard. I'm not sticking to that. You can still upload just in the next day or two, okay?
So if our partner turned in our lab and it says that mine is missing,
that's okay. As long as I've got one for the group, as long as all the names are on it, then I know that it's been turned in, okay?
So what's this going to look like before tomorrow? You said that there should be a kind of 4 hours.
Yes, I'm going to talk about that right now, okay? As I said in an earlier class, this class, Physics 110C, has always been designed for 4 classes a week, 4 hours a week of class time. And it's always been that way, except this year because of Corona. And normally that 4th day has been Thursday. And so in normal times, we would meet for an hour on Thursday as well as Monday, Wednesday, Friday. And the whole structure of this class is built on having that 4th hour each week. So the way I'm doing that, implementing that this semester, is the Thursday class is all videos. And there'll be 2. All right? First, there'll be the pre-lecture video, which I'll be sending you today. This will be for tomorrow, just as if we were going to have class tomorrow. Does that make sense? There'll be that. Then there'll be the class video, which would be the equivalent of if we were here. And you'll watch that after the pre-lecture video. Does that make sense? And that is our Thursday class. But you do it on your own time. But do try to set aside some time on Thursday to do it, because Friday's class will be predicated upon the assumption that you did Thursdays. Is this making sense? It's a little different because of the situation we're in. Okay. Yes?
Will Friday have a pre-lecture video as well?
Yes, it will. Because the Thursday class is meant to be like any other class, except the class part will be you watch another video. Okay. But there's content Thursday, like we would have had any regular class, and Friday just keeps building on top of what Thursday did. Okay. So look for the email to come to you later today with the 2 videos and links to them, the pre-lecture video and then the class video for Thursday. And then yes, on Thursday, I'll send you a pre-lecture video for Friday. And this is will just keep rolling along. Okay. Okay, next thing. You might have noticed there's a schedule for this class on Blackboard. If you were looking at the various documents, I know there are a lot. But if you look on our class on Blackboard, you'll see it's got a schedule. That might help you plan. It shows the whole semester, week by week. What chapters we're covering, when homework is due, and when we're going to have quizzes and tests. Of course, all that is also discussed in the syllabus. Nevertheless, our first quiz is this Friday. Here's how it's going to work. It's going to be a Wiley Plus type problem. In fact, it's going to be based on one of the Wiley Plus problems that's due Thursday night. So what's the set you're currently working on? Okay. And we'll have finished Thursday night. Friday's quiz will be based on one of those homework problems. I'm going to take it and I'm going to massage it a bit, change it up a little bit, because I don't want you to just memorize answers to problems. You're not learning any physics if you do that. I want you to do the problem so that you understand. How, you ask, do I know if I understand a problem? Here's my way to measure it. Could you turn to somebody else in this class and explain to them how you solved that problem? And the explanation cannot be, well, I'm not sure why, but I just discovered that if I use this formula and plugged in the numbers, Wiley Plus said it was right. But I'm not sure why. That's not understanding. Does that make sense? Okay, so the quiz on Friday will be based on one of the Thursday problems. Here's how I plan to do it. Again, different because of Corona. It will be posted on Blackboard There's a folder that says quizzes. You may have noticed it. It's already there. You go into it. This will not be done in class time. This will be done in your own time. It's like a take-home quiz. You open it, right? You access it. It'll just be a series of questions. You get a clean sheet of paper and you do all your work showing the answers. Make sure your name's on it. Snap a picture, scan it, make a PDF, and upload it onto Blackboard. And you've turned in your quiz. Now, here's how I'm planning on doing it. I'll let you know Friday in class if this changes because Blackboard doesn't cooperate. The plan is that it will be available starting roughly at about 9:30 in the morning on Friday, not tomorrow, Friday, and be available at probably until well in the evening. If possible, once you access it, Blackboard should know when you open it, you'll have 2 hours to upload your answer. You see what I'm saying? Mm-hmm. Okay. And that's how you'll do a quiz. What I plan to do on this first one, because things could go wrong, just this first one, any points you earn, I will just add as bonus to your quiz score at the end of the semester. In other words, if you don't get any of the points or you don't get all the points, it's not going to hurt you. Whatever points you get are just going to help you. But that's just so that we can get used to this whole procedure. And you're not feeling stressed about, oh, points, 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 while you're also trying to learn how to navigate Blackboard. And that I can't promise that there won't be some kind of technical glitch that we'll have to deal with. If anyone asks me a question about that, I'll say more about it again in Friday's class. Okay? Okay. You can always email me during the course of the day if something dawns on you later that you want to ask about. What I want to do now, though, is I want to do fun stuff. I want to get back to doing physics. Okay? And so let me remind you of the example problem that I had started at the end of class on Monday, because I want to pick right up there and move right along. This is an example problem where we were using the concept of instantaneous velocity. And in the problem, I'll remind you what the word said. We have two particles, a toy truck and a toy plane, both moving along a driveway, which we're calling an x-axis. And we are given the x-coordinate of the truck and the plane as functions of time. And they're just given to us, where x is in meters and t is in seconds. And as I said on Monday, that means you should be able to figure out, like that number 2, what units must it have if the x is in meters and the t is in seconds? And that point 4, what units must it have? And so forth. Because the problem doesn't show the units on those numbers, does it? Yet they do have units. That's going to be typical for these books, for the textbook. Okay? So that's what we're given. In fact, I drew the t equals 0 sketch because you could tell from these formulas where the truck is and the plane is at any time. And here they are at t equals 0. See where they are? Trucks at the origin, planes at 4 meters. Here's the first question. At what instant, t, do the truck and the plane have the same velocity? Velocity. That means I need a formula for the velocity, yes? For each thing. Notice how I'm going to label these things. Vt for the velocity of the truck. So who can tell me how I'm going to get that formula? Yeah, Drew. For the truck. So notice how I'm going to write it. dx truck over dt. Got to label things carefully, especially when you've got multiple particles. Now, we talked Monday about how you use what I call the polynomial rule for doing a derivative, because those are just polynomial terms there. So has anybody worked out what the formula is for the velocity of the truck, given this formula for x truck? Mm-hmm. 2 minus 0.8 t. There we have a formula for the velocity of the truck valid at any time. Now let's find a formula for the velocity of the plane. Notice what we have to do now. take the derivative of x plane with respect to time. Somebody want to tell me what you got for that? Gabriel. Negative 1 plus 0.5 t. Okay? Now, if that's not clear to you, you might want to go back to the notes on Monday and look at the polynomial rule and practice some more with it. Okay? Because that is the kind of derivative you need to be able to do in chapter 2. So how do I find out when t, the velocities are equal? What do I do? Here. Set the formulas for the velocities equal. Right? That's what it means in symbols. So take the formula for v truck, 2 minus 0.8 t, and set that equal to v plane, minus 1 plus 0.5 of t. Now you ought to be able to solve that for t, yes? Let's see. Let's take the negative 1 over. It becomes plus 1 with the 2. That leaves me a 3. Let's take the negative 0.8 t over there. It becomes positive 0.8. I think I'm left with 1.3 t. By the way, I'm going to do algebra fast. If that's a little too fast for you, go back after class and make sure you can do those steps for yourself at your own pace, but you got to be able to do them. And if you ever see that I made a mistake, by all means, point it out to me. Okay. Now you see what you do next, right? Divide both sides by 1.3, and you'll have the t. I get that that's 2.31. Give 3 sig figs and give units. Seconds. You must put units. Yes.
So, in terms of how you want us to format these questions when we're doing them for like assignments and stuff, I'm assuming there's more parts to root A. So, and I'm assuming also that we might need that number at a later point.
Mm-hmm.
Do you want us to also write it with extra trailing numbers?
Well, I have found in the past that if you give at least 3 sig figs, you're fine on later parts, generally speaking, but never around less than 3. Then you quite likely are going to go outside of Wiley Plus's 2% tolerance. Even though you may be doing it technically correct, you've rounded out of the tolerance. Okay. Note, by the way, that's when they have the same velocity. I think it's useful to sketch their velocities in our t equals 0 picture. Let's do that real quick with arrows, because I can do that from the velocity formulas, right? Like the truck's velocity. What is the truck's velocity at time 0? Positive 2 meters per second. Positive 2, right? So I know the truck is moving in the plus x direction at a rate of 2 meters per second. So I can draw an arrow pointing to the right and label it V truck, and I put a 0 on it, initial. Okay. What's the velocity of the plane at time 0? Negative 1 meter per second. So which way is the plane moving? Negative x at half the rate of the truck. Yes, half of the rate. So draw an arrow half as long, roughly. V plane initial. So notice what they're doing at time 0. They're on a collision course, aren't they? Whatever kid is playing with these two is about perhaps to crash them together. Well, in any event, we've answered part A. At that particular time, they have the same velocity. Now comes part B. Oh, I'm sorry, I don't want blue, I want black. Part B. I'll just read it to you. What is the common velocity at that time 2.317? Right? That's the time when their velocities are equal. What is the velocity? Any thoughts on how you would do that? Mm-hmm. Just plug the t in for either velocity, yes? Because for that one moment, they're equal. So I plugged into the truck one, 2 minus 0.8 times t 2.31. This has got to be a V, so it's got to be meters per second. I get positive 1.54 meters per second. So 2.31 seconds after this picture, right? This is t equals 0. Which way are they moving? That way. So what has this one done? It's reversed, hasn't it? Because initially it's going to the left. Now it's going to the right. It must have reversed. But you've answered B. C. What is the maximum value of X truck? Of X truck. Okay? Apparently, the contention is that the truck goes this way, but goes to only some maximum location before going back, apparently, right? How are we going to figure that out? Well, everything we need to know about X truck is in this formula. Everything. I recommend drawing a sketch. Let's sketch this. What shape is that? If I plot X truck versus time, it's a parabola. So we're going to sketch X truck versus time in seconds. It's a parabola. In fact, because of the negative sign on the square, it's a parabola that opens down. I know at time 0, X is 0, so it starts right there. You can also solve and figure out that there's another time when X equals 0. Just from this formula, there's another time when X equals 0. I will tell you what it is. It's 5 seconds, just from that formula, okay? So I'll put a 5 here. And so there's another time. And it's a parabola that opens downward. It's just a sketch. Must be something like that. Yes? And sure enough, there is a maximum. XT max. Yes, I know that powered off. I have to find that max, don't I? That's what it's asking. What is XT max? The sketch might help. Now, you might have a gut answer. I'll ask it anyways. When do you think that occurs? What t value? 2.5. Midway? But maybe we better figure out how to figure out exactly. Well, the maximum, of course, is where this is highest. What if I follow this curve with my hand following the slope of it? What's the slope of my hand when I'm at the highest point? 0. What is the slope of the tangent line on this graph called? Velocity, right? Plot of position versus time, the derivative is velocity, derivative is slope of the tangent. So right here, where the tangent line has 0 slope is where the maximum is. It's where the velocity is 0. That makes sense? This problem requires you to be able to reason that out. So to find that V truck max, I need to find out when, it's going to be X trucks max, I need to find out when V truck equals 0. Well, I already got the formula for V truck, didn't I? 2 minus 0.8t. So I want 2 minus 0.8t to equal 0. I think I can solve that for t. And sure enough, you get t equals 2.5 seconds. So that is when X truck peaks. But that's not the answer, is it? Did it ask when X truck is a maximum? It asked what is the maximum value of X truck. So what do? I plug that time into the position formula for X truck, right? X truck maximum, where's X truck? Right there, 2 times T. For the T, you now put in 2.5 minus 0.4 times T squared. So 2.5 squared. Don't forget to square that factor. And then just plug in your calculator. I'll tell you what you get. You get a lot of 2.5s, but that just is happenstance. 2.5 meters is X truck maximum. That's right about there, isn't it? So that's apparently as far as the truck gets. And after that, what does it do? It goes in reverse, right? What's that? Turns out both of them do. Yes, that's what the formulas are telling us. All right? They start out going towards each other, but they both reverse. Okay?
On a quiz or test, would we be allowed to use a graphing calculator to check that?
I'm okay with that. Okay? There, everybody's kind of on their own. Some don't have graphing calculators, some do. You're never going to turn in your work from the calculator. So yeah, it's okay with me. If I were teaching an Algebra 1 class, that might be different. All right, D asks, do they collide? Oh, well, they are moving towards each other initially, aren't they? See, aren't they traveling towards each other? If I'm the parent watching the child play with these things, I'm thinking, well, there goes that money, because they're going to crash them together. Okay. Well, let's see if they do or not. Apparently, if left to their own devices, they'll each end up going back the other way. But we don't know for sure that before they get a chance to do that, they do that. Isn't that right? Just think about this scenario in your head. So, do they collide? How would we answer that question? Watch out, it's a little bit subtle. Giving you a heads up. Having said that, very few takers now. You want to try?
Whenever we have the implicit time, 2.31 is the graph or that's the time we would.
You want to use the 2.31?
Yeah.
Well, that's when they have the same velocity, right? But I want to know if they collide with each other. Yeah, go ahead, Drew.
Couldn't find where the velocity equals 0 of both of the speed of the velocity, where the plane turns around to the left.
Okay. That's the answer I expected, but thank you. I think there's a slight flaw. I think what you're saying, let me see if this is what you're saying. We know the biggest for X truck. We could figure out how far X plane gets that way. And if they overlap, they must have collided. I think there's a slight flaw in that, unfortunately.
Can I answer? Is there anyone who tell me?
I got somebody talking in my ear. Is that Salim?
Yeah. We can check if they go to the
I
same.
think that's what Drew said. Salim's telling me. Say it again, Salim.
If I could, we could check if they are at the same position.
Are they ever at the same X? That is what collide means, does it not? Same X at the same T. I should be careful. Same X at the same T. That's technically what colliding means, yes? You are in the same place at the same time. That's important. So let's take the X for the truck and set it equal to the X for the plane and solve for the time. Let's see if there is a time when that's true. You see what I'm saying? Now, why doesn't the other argument work about finding where, where each of the things has an extremum and just seeing if they overlap? If that's what the truck looks like, what if the plane graph looks like this? Could be. Now, you see the problem? X trucks max is bigger than X plane min. So their extreme points overlap. But do they collide in that case? No, because they were never at the same X at the same time. What does collide look like if I plot both X graphs together? What does collide mean? They cross. Yes? That's what collide means. They cross. Now, time is ticking away, so here's what I want to do on this last part. I want you to do the math on this part D. It's a little bit challenging, but it's good practice. Take the formula for X truck. There it is. Take the formula for X plane. Set them equal. Will not the only unknown then be T, time? Right? The only unknown will be little t, time. And you have to solve for a little t. Now, notice, each of those equations is quadratic in t. So how are you going to solve the resulting formula for t? Say again? If you're lucky, it'll factor. Guess what? This one won't factor. What's the way you know you can always use? What is it? I thought somebody said it. Quadratic formula. Remember that? Handy thing. We're going to use it a lot. Although it is high school algebra, so I'm not going to go through that, okay? Just use the quadratic formula. Now, you can learn some real physics here. You can use the quadratic formula. It will give you two answers for t, right? Every quadratic equation has two answers. How do you know then from your answers whether the things have collided or not? Yeah. Not necessarily. Well, the t value I get from the quadratic formula must be real. Oh, do you remember imaginary numbers? Square roots of negatives? Quadratic formula is going to give you a square root with a negative sign in it in this case. I'm just telling you. That means the answer is said to be a complex number, not a real number. That's the math telling you it doesn't physically happen. Oh, wow. Okay. So when you solve this for t using the quadratic formula, the t answer you get is a complex number. It's got a square root of a negative. That means it's not physically possible. Does that make sense? The math will tell you a lot if you learn to interpret its signs that it's giving you, or clues, maybe I should say. All right. I need to move on, folks, because I want to start talking about acceleration. So let me power up. Okay, it's coming up. You worked with acceleration, of course, in lab. Let's reinforce some of the things you were learning there. First, let me give you the learning objectives. When we were talking about acceleration, we need to be able to apply the relationship between a particle's average acceleration, its change in velocity, and the time interval for that change. There's the formula that was in the pre-lecture video for today. A average is delta V over delta T, change in velocity over change in time. Next, given a particle's velocity as a function of time, calculate the instantaneous acceleration for any particular time. That's just A, instantaneous, and it's another one of these limits as delta T goes to 0 of delta V over delta T, and that becomes a derivative. Instantaneous acceleration is the derivative of the velocity with respect to time, or the rate of change of the velocity. And you need to be able to work with graphs. If we give you the particle's velocity versus time, it's a little hard to see, but this is a velocity time plot, and it looks like that. You are supposed to be able to determine the instantaneous acceleration for any particular time and the average acceleration between any particular two times. So if I give you a plot of V versus T, just from the graph, how would you find instantaneous acceleration if I picked a time, like right there? Yeah, Adrian. Slope of the line, right? Derivative is slope of tangent line. Acceleration is derivative of velocity with respect to time. So you give me a plot of velocity versus time, the instantaneous acceleration is the slope of the tangent line. So you could follow your hand along this graph and see how it slopes, and that's A. So right here, the slope is 0. Now the slope is positive, and given the grid lines and a good image that you can actually see, you can do rise over run and get that slope, yes? And get the acceleration there. What's the acceleration of the particle on this part? 0, right? Because your hand is horizontal. Then you go down steeply, but negative here, don't you? So the acceleration here is negative. In fact, it drew that graph for you. What if I asked you to find the average acceleration, say, between t equals 1 and t equals 5? Again, that may be hard to see. There's t equals 1. There's t equals 5. From the graph, what would you do? Slope of that line, connecting the graph at t equals 1 to the graph at t equals 5. That's the average acceleration. Okay. Hint, hint, that's going to be a very handy idea for one of the Wiley Plus problems for Thursday night. Okay, with that in mind, remember, if you watch the pre-lecture video, all these ideas were already discussed. Okay. Let's start using them. Let's start practicing. This figure shows 4 different plots of velocity versus time for a particle moving along an axis. The plots are combined all together on the same axes, right? There's 4 of them, all on the same set of axes. But each plot's labeled, right? There's an A and a B and a C and a D. Plots A and B are in what you would call the first quadrant, and C and D are in the 4th quadrant, if you think of that as a coordinate plane. For this question, two of the important phrases we're going to use are speeding up and slowing down, which we also were trying to get you to use in lab this week. Speeding up means going faster and faster and faster. That's what the phrase means. To be more specific, it means the magnitude of the velocity is getting bigger. Magnitude. Slowing down means you're going slower and slower and slower. The magnitude of the velocity is getting less. Okay, all right, here come some questions. I want us to think about these. First, A, which of the 4 plots represents the motion of a particle that is speeding up during this interval? So you can think about it a second. Okay. What I'd like you to do is turn to the person nearest you. You can't get too close. Just say to each other what you think the answer is. So turn to behind you, to your left, to your right.
Right, and then if we see the cross section, see. Well, because. Yeah, it's it has to because slope is going.
Okay. Have you converged on an answer or answers? Which plots represent the motion of a particle that is speeding up? Anybody want to volunteer? Yeah.
B and C.
B and C. So the one that's going up like that into the first quadrant, and the one's going down like that into the 4th quadrant. Because in both cases, the magnitude of the velocity is getting bigger. The sign of the velocity is just telling you the direction it's going in, right? For part A, I don't care what direction it's going in. I just want to know, is it going faster and faster? Yes? All right, B. Which plot of plots represents the motion of a particle that is slowing down during the interval shown? So that maybe goes a little bit quicker. Do you have a thought? A and D. Because in each case, the magnitude of the velocity is going to the center line here. What does that mean? because that center line means the velocity is 0. So both of these have magnitudes of velocities going to 0. That is exactly what slowing down means. All right, so let's keep track here real quick. This is practice number 1. So which ones were speeding up? B and C. Which were slowing down? A and D. All right, next, C. Which plot or plots represents the motion of a particle that has positive acceleration based on the graphs? Somebody. Yeah.
B and D.
B and D. Now, what is that answer based on? Slope, right? It says positive acceleration. Acceleration is slope of tangent line on velocity time plot. Which graphs have positive slope? Period. Okay. B and D. Everybody understand that? Aha, note something. D. Positive acceleration, right? But D also showed up here, didn't it? But that was slowing down. Ah, you can have a positive acceleration and be slowing down. All right, what's the last one? Which plot or plots represents the motion of a particle that has a negative acceleration? Okay. A and C. Okay, because the line has a negative slope. Negative acceleration. Oh, but wait, C. The C showed up in the speeding up case, didn't it? There's a case where you have a negative acceleration and it's speeding up. Watch out for that. A lot of people want to say, oh, positive acceleration means speeding up and negative acceleration means slowing down. Not necessarily. How do you know? If I give you the velocity and acceleration, just the numbers for V and A for a particle, how can you tell if it's speeding up or slowing down? Yeah, Adrian.
Depends on the time.
Okay.
The velocity and acceleration at the same time, and they're speeding up at different times.
That's right. If the velocity and the acceleration have the same sign, the particle is speeding up. If the velocity and acceleration have opposite signs, the particle is slowing down. The reason is acceleration is rate of change of velocity. So if the acceleration and the velocity are in the same direction, then that's making the change in V bigger. But if the acceleration and the velocity are in opposite directions, that's making the change in V less. All right, let's do a little more practicing because I want you to be comfortable with velocity time plots. This one's even a little more subtle. It's only just one graph though. It goes like this. We are given the velocity of a particle. I don't know what it is. It's moving along an x-axis, but notice what we're given. The graph is velocity versus time, not position versus time, velocity versus time. Just to be clear, the point 1 is on the highest point. I guess that's pretty clear. Point 4 is the lowest point. Points 2 and 6 are at the same height. We want to be able to interpret how this particle is moving along. It's moving along an x-axis, right? This is an abstract way to represent what its velocity is doing with time. So here's the first question, A. What's the direction the particle is traveling on this x-axis at time 0? Trying to let some people answer maybe who haven't. You want to answer? It's going in the positive direction. How do we know? Go time 0, see what the velocity is. If it's a positive number, the particle is moving in the plus x direction. The sign of the velocity tells you which way the thing is moving. Which way is the thing moving at point 4? Which direction is it moving on this x-axis when we're at point 4? Yeah. Here? No, it is. Aha, negative, right? This is velocity versus time, not position. And 0.4 is clearly below the axis, right? The horizontal axis. That means you're in negative territory on the V. So the V here is negative. So it's moving in the negative X direction. Everybody understand that? Next question. At which of the 6 numbered points does the particle reverse its direction of travel? Meaning if it was going in positive, it goes negative, etc. 3 and 5. What is the velocity at those actual points? 0, yes? Because the curve intersects the time axis, that's where the V is 0. So that point and that point means V is 0. That's what the V's got to be if it's doing a turnaround. So here, just before, the velocity was positive. At this moment, the velocity is 0, and then a little after that, the velocity is negative. So it's changed from going this way, stops for an instant, and then it goes backwards. Just the opposite happens at 0.5, right? Right before that, it's traveling in the negative direction. Stops for a minute, and right after that, it's traveling in the positive direction. So it's doing this. All that you can visualize from that graph. Let's do another one. This one's a little more challenging. Rank the 6 points according to the acceleration value of the points. The way you do the ranking is the most positive acceleration goes first, and then get less and less and less, go into negative territory, and give the most negative acceleration last. That one you may have to think for just a moment about. You have a question?
Are we allowed to set semicolons equal to each other?
There may be ties. In any of the ranking problems, ties are always a possibility. C is the one we're on. Neither of these pens is very good. Let's start, maybe we'll start. Can anybody think, what's the biggest positive acceleration here? Which point? Yeah.
2 and 6.
Almost.
Or 6.
6, there you go.
Sorry, I thought you just meant which. If you, sorry, I didn't realize you were talking about sign. I didn't. Yeah.
Okay. Here's the hint. Most positive first, most negative last. Also, but you're right. We could very well have said, don't worry about time. Then you know how it would have been worded? Rank the 6 points according to the magnitude of the acceleration. Greatest first.
Is there a word like speed for acceleration?
Oh, you mean, is there a word for just the magnitude part of the acceleration? Interestingly enough, no. Yeah. There is a word for the derivative of acceleration with respect to time. Jerk. That's not an insult. That's the word for it. Okay. All right. So the biggest positive acceleration is for points. This is a terrible pen. Yeah. These are not very good. A6. Okay. What's the next biggest one? A little subtle. Thought? It's 5. We're just talking about slope of the tangent, aren't we? Everybody see that? Acceleration is slope of tangent. The slope here is a little less steep than here. You have to look at it pretty closely, but it is. Okay. So A6 is a little bit larger than A5. So there's how you could write it. What's the next one? They're both 0. And they're the same. So next is 4 and 1. Here's how I would write it. A1 and 4 are equal. What's the next one? Remember that we have to end up with the most negative one. So basically you're looking for one that's negative, but not the most negative. 3. It's clearly a negative slope, right? Your hand slopes down there. Turns out it doesn't slope down as much as it does at 2. So next you would put, I'll write it here, A3, and last you would put A2. Another way you could write this would be like this. 6, 5, 1 equals 4, 3, 2. It looks kind of odd, but that's another way you'll see people give ranks. Let's do this last one. At which point is the particle speeding up? Or points?
From 3 to 4.
From 3 to 4, because the magnitude of the velocity is 0, and then I have more than 0 magnitude, right? Speeding up just means the magnitude of the velocity is getting bigger. Yes, that is true, right? Velocity is 0, and then the velocity magnitude is not 0. Is there another one? Well, we're really just picking a point. 6, okay? 6, because the velocity is positive and the acceleration is positive, it's going up, isn't it? The magnitude of the velocity is getting bigger, it's speeding up. You could even argue 5, because the velocity is 0 and it's getting bigger. What about slowing down? 2, did somebody say? Right? Velocity is positive, acceleration is negative. If V and A have opposite signs, it's slowing down. Okay. All right, last thing for today, and then we'll stop. This is what I'm going to do first on Friday's class. I'm going to do a Wiley Plus problem that uses these famous equations. Again, if you watch the pre-lecture video for today, I talked about them in quite some detail. They're called the constant acceleration equations. Very handy kinematic equations that you can use to study the motion of a particle if the particle's acceleration is constant. Okay? I call them constant acceleration equations 1, 2, and 3. V final equals V initial plus A times T. X final equals X initial plus V initial T plus 1/2 AT squared. V final squared equals V initial squared plus 2A delta X. The key thing about equation 3 is it does not have the time variable. And for some problems, that's going to be a handy equation to use. Okay. We're going to do a Wiley Plus problem using these. And Thursday's lecture videos are going to also use them. Okay? Okay.
Professor,
Yes.
is the class dismissed?
The class is now over.
Okay, I have a question,
Yes.
if I may.
Let me
So
stop the
when we were
recording
doing,
here. Just a second.
okay.